Imagine if you have like a scenario in which you have multiple crowd of people walking in a subway station. And if you want to track a particular person, there needs to be a specific way of doing it. So multiple object tracking is just tracking a set of objects, which we can identify from images and videos. And these are not just images and videos, but since we are mainly concerned with videos and images here, so the tracking that I'm talking about is in context of the image and videos. So when you detect these, the path of these specific objects, as you can see over here in this video, there is a lot of cells that are moving in a field of view, and you can clearly see that these have been tracked. So each of these tracks form a tracklet. Tracklet is basically just a container which contains the history of the object that you're tracking. Other areas where like tracking is really important is when you have, for example, self-driving cars or autonomous vehicles. Surveillance is another thing for military purposes, for sport analytics. For example, if you have to follow like players playing basketball in a field, then in case of for scientific purposes, like from my own background, it was critical for us to be able to track different objects under the microscope. And it does not just pertain to the world of the very small, but also to the world of the very large that we can observe with the telescopes. Computer vision and robotics is another prime example where object tracking is really important. Yeah, so the idea I've already told you what tracklets are. So it's just a trajectory of the different objects, of uniquely labeled objects. So imagine if we have 3 objects over here, then and these set of points are representing objects and at different time points. Then if you are able to link these objects together, you form a tracklet. These tracklets can be contiguous, as over here, as you can see, for example, 3, 7, 11, 15, 19. If you can follow this is a particular tracklet. Or they can be broken. So over here, for example, 1, 4, 9, and somehow over here, you cannot link it back to the object number 18, and instead some other track managed to join object number 18. So objects, as you can see, can get lost in a crowd or can be occluded or obscured by some other object. If some other person steps in front of you, then you're lost in the image or the video. So this kind of occlusion can be either permanent or temporary. And handling this particular issue of occlusion is really is a big challenge. And for example, I've already given you a quick example, that 1, 4, 9. And if there was a way to handle occlusion, then 9 could have been connected to 18. But for the purpose of the example, this came out to be a broken tracklet. One way we can handle occlusions and deal with these subtle challenges is by using something which is known as a Kalman filter. So people who have a bit of background in physics or electrical engineering or any form of engineering, they use Kalman filters a lot. And Kalman filter is nothing but just a Bayesian scheme that enables us to make better predictions by integrating some measurements from the surroundings, from the different sensors. So imagine if this is the prediction that you're making of a car's location. This is the prediction. That's a pretty poor prediction. But if this is the measured state, or this is, let's say, the actual state of the car, which is this red, then if we have some kind of a model if we integrate this measurement as well as a prediction, we would be able to get a better idea of where the state of the car is. So using these Kalman filters, we can handle occlusions and misses. So the algorithm that we are talking about is based on the original sort algorithm, and the original sort algorithm has been updated by using Kalman filters in a much better way to handle occlusion. And the linear motion model assumption has been used in this Kalman filter to deal with occlusions and nonlinearities for this kind of algorithm that we are using at behind for object tracking, which is OC sort. Which means observation-centric, simple, online, and real-time. It's a very big name, but it's quite easy to follow. So what we do is in the first round, when we have, let's say, a given set of predictions given in magenta, and then you have objects that are being detected shown in green, we want to associate our predictions with the detections. So one way is to look at how much of the predictions have overlapped with these green boxes. So how much of magenta is overlapping with green boxes, and using this and the direction in which the objects are moving, using that we can construct something which we call as a cost matrix. So it's the cost of association of associating one object to another, and it's given as a two-dimensional matrix. Then we can use some kind of an optimization solver, or we can solve it via some form of optimization. It's an optimization problem, so we have to minimize the cost and then have predictions assigned to the detections. So we use over here solvers like linear assignment problem, or you can use find independent edge sets, or some other graph theoretic approach to solve the problems. At the end, what we have after end of round one, what we have is a set of paired detections, so things which have been successfully linked between magenta and green. But on the other hand, there are objects from magenta that could not be associated with the green over here, or on the other hand, some detections that are green or are measured state, which could not be associated with the tracklets, which are the unpaired detections. So this is the first scheme, the first part of the algorithm. So the second round is also quite easy to follow. So what we do is we try to find potentially lost tracks or reconnect any broken tracklets that are there. So by broken tracklet, I've already shown you that tracklets that were not associated or linked to any detections for the previous time step. So what we do over here is we create another cost matrix for the last bounding box that was ever linked from the remaining tracklets to the remaining detections that were not associated. And by doing this, we construct another cost matrix and do another optimization on the cost matrix. And then we get another set of pairings and unpaired tracklets, as well as the last unpaired detections. So finally, we have the successful pairings, and then we have the unpaired tracklets and the unpaired detections. In round three, which is very simple, is that we need to initialize new tracklets from the detections that remained unassociated even till the very end. And for the unmatched tracklets, we just remove or delete them if they have expired. So let's say if we consider that any tracklet that has not been associated for 4 frames or 3 frames is old, then we kill that tracklet off. But the interesting part of the algorithm is which makes it quite powerful, is that is what happens when we update the status of the tracklets. So if the tracklet is like contiguous, if it was already contiguous, and so what we do is we just get this measurement state, update our Kalman filter parameters, and then the detection on the green box is basically saved in the tracklet's history. But if the tracklet was initially not associated, but now it's matched, so what we do is we roll back from our predicted state all the way back to the last state, to the last bounding box, last match bounding box. And then from here, we do an update of our Kalman filter parameters. And by doing this kind of re-update, what is good about it is that any future potential future misses can be avoided in this case. So by doing this kind of a re-update scheme, is what the authors of OSI sought. By doing this kind of re-update, they managed to bring the efficiency up for the association part of the algorithm. So and the detection is then saved in the tracklet's history. So by doing several rounds of this, so we are able to kind of generate all the tracks, like whether there are thousands or hundreds of objects.
So how is this used in Mathematica? Well, we introduced a video object tracking function that can track different data types. In this case, I'm tracking the boxes that were computed in the previous one using image bounding boxes. And you can see if I highlight the result of that, each car has a unique identifier. The tracking knows about which car is which. video object tracking has multiple input types. It can work on bounding boxes as rectangles or points or label matrices. Here I'll show, there's a quick example that shows tracking on a video using label matrices. This is the original video. This is the track video. You can see how the color jumps around much less. If the input is a video, the detection is performed automatically using image bounding boxes. And I'll jump back to the result. And you can see here the result of the tracking, all the history of each of the tracklets. You can provide a custom detection function if the input is a video. In this case, I'm using YOLO V8 from the net repository, performing the same tracking. And you can see here how this returns a lot of results, and the tracking is very consistent. You'll also notice how video object tracking returns a specific object. It's called object tracking data. It contains all of the history of these tracklets and various properties, which you can extract using the subvalue syntax. In this case, these are all the tracklets. They are the bounding boxes for all the tracklets. You can get positions that are the centroids of those bounding boxes. In this case, you can look at derivatives of those. Again, there's a collection of properties that can be interesting. You can filter for specific keys. In this case, I want only cars number 4, 3, and 1. So this object tracking data only contains those. And selection and property extraction can happen at the same times. It also has video-specific properties. In this case, for each label, you can extract the video, the sub-video that corresponds to it. And the data itself can be transformed to different formats. Tabular, which was introduced in version 14.2, is an extremely useful and powerful one. Dataset is supported as well as time series.